Have you ever watched a master chef at work? They use recipes and techniques, proven solutions to common problems. In software, programmers have something similar, design patterns. Think of them as a secret language, a set of time-tested solutions for recurring problems in software design. When a developer says, "Let's use a factory here," everyone knows what to do. These patterns help us build better, more maintainable software, no matter the language or project. So, let's learn the secret handshake of expert developers. Why care about design patterns? Imagine building a house with no plans, chaos, confusion, and instability. Software is no different. Without blueprints, code becomes a tangled mess, hard to maintain or grow. Design patterns are proven solutions, battle-tested strategies that save time and prevent common mistakes. They give teams a shared language, making collaboration and onboarding easier. With patterns, your code is flexible, reusable, and built to last. Let's start with creational patterns. These are all about how objects are created. Sometimes object creation is complex or needs to be flexible. The factory method lets you delegate the creation of objects, so your main code doesn't need to know the details. The builder pattern helps construct complex objects step by step, like building a custom pizza. These patterns make your code flexible and maintainable. Add new types without changing existing code. The singleton pattern ensures a class has only one instance and provides a global point of access. Think of things like a print spooler, a logger, or a configuration manager, components that should be unique. The trick is making the constructor private and using a static method like getInstance to control creation. But beware, singletons can lead to hidden dependencies and make testing harder. Use them only when something truly must be singular. Otherwise, consider alternatives like dependency injection. Structural patterns are all about composition, assembling objects and classes into flexible, efficient structures. Think of it like building with Lego bricks. You can combine and swap pieces easily. The decorator pattern is a great example. Start with a basic coffee object, then wrap it with decorators like milk or sugar. Each decorator adds new features, but the object still looks and acts like coffee. This is the power of composition over inheritance, adding behavior without changing existing code. The adapter pattern helps mismatched parts work together. Just like a travel power adapter lets your charger fit a foreign socket. In software, it bridges incompatible interfaces, letting new or legacy code collaborate seamlessly. You create an adapter class that wraps the incompatible object and exposes the interface your code expects. The adapter translates calls, so your system works smoothly, no matter the language or legacy code. The adapter pattern is a simple, powerful way to integrate components that weren't designed to work together. Our final category of patterns is the behavioral patterns. If creational patterns are about birth and structural patterns are about anatomy, then behavioral patterns are about communication and interaction. They are concerned with algorithms and the assignment of responsibilities between objects. These patterns describe not just the structure of classes or objects, but also the patterns of messages and communication between them. They help make complex control flows easier to manage and understand by defining how objects collaborate to perform a task that no single object could carry out alone. A classic example of a behavioral pattern is the strategy pattern. Imagine you are developing a shipping cost calculator. The cost might be calculated differently based on the shipping method: standard post, express courier, or international freight. You could write a big if-else or switch statement inside your calculator class. But what happens when you need to add a new shipping method, like drone delivery? You'd have to go back and modify that complex conditional logic, which is risky. The strategy pattern suggests a cleaner approach. Define a family of algorithms, encapsulate each one, and make them interchangeable. With the strategy pattern, you would have a shipping strategy interface with a single method, calculate. Then you would create separate classes for each shipping method: standard shipping, express shipping, international shipping, each implementing the shipping strategy interface. Your main shopping cart class doesn't perform the calculation itself. Instead, it holds a reference to a shipping strategy object. When it needs to calculate the cost, it simply calls the calculate method on whatever strategy object it currently holds. To change the shipping method, you just swap out the strategy object. This follows the open-closed principle. Your shopping cart is open for extension, so you can add new strategies, but closed for modification. This pattern is a perfect fit for object-oriented languages like C++ and Java. You define an interface strategy and then implement it with various concrete classes. The context class holds a pointer or reference to the interface. In C, you can achieve the same result using function pointers. The context struct would contain a function pointer for the calculate operation. To change the strategy, you simply point this function pointer to a different function, like calculate_standard or calculate_express. Behavioral patterns like strategy are fundamental to writing clean, flexible code that can adapt to changing requirements without major surgery. The observer pattern keeps everyone in the loop. When one object changes, others are notified automatically. Think of a newspaper publisher. It just publishes news, and subscribers get notified when there's a new edition. In software, the subject maintains a list of observers. When its state changes, it notifies all observers, who update themselves. This is the backbone of event-driven systems, like spreadsheets, where charts update instantly when data changes. We've journeyed through the world of design patterns, from the creation of objects to their structure and their behavior. We've seen that these are not rigid rules or specific algorithms, but rather flexible blueprints, proven recipes for solving common software design problems. They are the shared language that elevates a programmer from a simple coder who just writes instructions to a software architect who thoughtfully designs systems that are robust, maintainable, and scalable. Understanding these patterns is a significant step in the maturation of any developer, regardless of whether they are working in C, C++, Java, or any other language. The benefits are clear and compelling. Design patterns lead to more flexible and reusable code. By promoting principles like loose coupling and favoring composition over inheritance, they allow us to build systems that can adapt to change. When a new feature is requested or a requirement is modified, a well-designed system can accommodate it with surgical precision rather than requiring a chaotic and risky rewrite. This saves time, reduces bugs, and ultimately leads to higher quality software. The code becomes easier to read and understand, not just for you but for your entire team. The examples we've explored, the factory, singleton, adapter, decorator, strategy, and observer, are just the tip of the iceberg. There are dozens of other documented patterns, each offering an elegant solution to a different kind of problem. The key is not to memorize every single one, but to understand the underlying principles. Learn to recognize the situations where a pattern might be applicable. When you find yourself writing complex if-else chains to handle different behaviors, think of the strategy pattern. When you need to add functionality to an object without subclassing, think of the decorator. Ultimately, mastering design patterns is about developing good design sense. It's about building a mental toolkit of solutions that you can draw upon when faced with a challenge. It encourages you to think about the structure of your software at a higher level, considering how the different pieces will fit together long before you write the first line of implementation code. By embracing these patterns, you are leveraging decades of collective experience from the global software development community. You are learning to build not just for today, but for the future, creating software that is truly built to last.